Hello, my name is Neil Morgan and I'm a geotechnical engineer and engineering manager for Lloyd's Register based in the UK. I'm part of a global team of colleagues that look at wind certification and offshore wind projects. I'm also chair of the Offshore Site Investigations and Geotechnics Special Interest Group for the Society of Underwater Technology that develops guidelines and other guidance for the offshore industry to follow, and that includes some renewables guidelines that I'll talk about later. And I'm also a member of the API ISO committee, which looks after offshore foundations content within API and ISO standards. And I have a special responsibility within that as chair of Technical Panel 4, which looks at the offshore pile related content within those standards. Today I'm going to present a general overview of offshore wind certification, but with a particular focus on the design basis stage and how it can really support execution of a successful project. A brief overview of Lloyd's Register is that we have approximately 8,000 employees worldwide. We've been in existence for more than 250 years. And through collaboration with clients and industry, we aim to advance knowledge and make sure that designs and developments are safe and secure. And we participate in quite a lot of different technology development projects, including those specific for offshore structures and also for offshore foundations in relation to the offshore wind industry. This slide summarises more than 20 years of involvement from Lloyd's Register in renewables and offshore renewables projects. We've completed offshore wind certification for projects within Europe, including the UK, Germany, Denmark, France, Belgium, and also further beyond that into Taiwan. We've looked at fixed and floating wind turbines and substations, and we're also currently working on one of the world's first floating hydrogen producing wind turbine projects currently. This slide shows the presence of Lloyd's Register in South Korea. We have offices based throughout the country and approximately 250 technical and administrative staff. Contact details for Lloyd's Register in South Korea are given on the last slide of this presentation. There's often the question of why you need to certify your wind project. Wind projects by their very nature tend to be very large financial investments with many different stakeholders, including the developers themselves, investors, national regulators, and also designers and consultants. There's a lot of different parties involved. And the investors in particular and other stakeholders need to safeguard that investment. And also the wind farm must comply with relevant national regulations and ultimately needs to get insured in the future as well. So wind project certification provides an assurance and risk mitigation for the entire project, and it can be broken down into modules, and it also successful development of a wind farm is vital for ensuring the profitability and future of offshore wind developments. I'll now present an overview of the IEC 61400-22 and IECRE OD 502 wind project certification processes. The overall process is split into a number of different modules, which you can see on the screen there in the blue rectangles, the solid blue rectangles. And these are mandatory stages in the project certification. The first stage is a site condition stage, and that's where the site condition data is reviewed to confirm it complies with the relevant standards and that there's sufficient data available for the wind farm design process to take place. We'll look at some of those in a little bit more detail later. The second module is the design basis stage, and there, in principle, the different parties involved in the design set out their assumptions and input data and methodology that will be used in the design process. The next stage after that is an integrated load analysis, where a combined system of turbine, structure and foundation is assembled and run to confirm the wind loading that will take place on the structure when it's in operation or when it's in service, basically. The next stage after that is the design evaluation stage, where each component in the whole system is looked at, including the wind turbine generator RNA, the tower, the support structure and the foundation. And there is also the possibility to cover other installations within the IEC or IECRE processes, and these include things like substations or cables. The next module that can be completed is a surveillance module, and this includes surveillance of manufacturing, transport and installation and commissioning. And the general principle that applies in this module is that what is being manufactured or transported or installed or constructed or commissioned needs to be in conformance with the design that's been accepted earlier in the process. The surveillance module in solid blue is also a mandatory module in order to complete project certification, and a project certificate can be issued after that stage. There are some further optional stages which could include operations and maintenance surveillance, and that could go on throughout the wind farm life. The aim of a design basis or a set of design bases is to define all of the inputs, the methodology and the assumptions that will be used in design. A good design basis should reduce project risk by providing a methodical approach that's defined for all of the different stakeholders. And those include the developers, the turbine suppliers, the designers, the installation contractors, and also provide assurance to investors that the development's taking place in accordance with accepted codes and standards. An important thing to understand early in the design basis stage is what sort of engineering concept is going to take place, whether it's going to be monopiles, jackets, floating turbine with drag anchors, etc. And also an early stage screening or an early stage confirmation that that concept or those concepts can be applied to the site in question. You should also define things like national requirements and codes and standards with a hierarchy in place. One of the things to emphasize with the design basis is that seemingly small topics at a design basis stage can have a big impact later on in a project if they're not resolved early and not resolved well. So yeah, to avoid something major later, fix it as soon as you can and preferably at the design basis stage. An interesting side note in the discussion of a design basis and also related to certification is that certification can provide a framework to achieve an optimal design. So you can take into account the latest industry practice or the industry developments and ensure that the design will be suitable and meet the codes and standards. So you're kind of balancing the need for the industry to become more efficient and include novel technologies, but also make sure they conform with kind of the basic requirements of established practice. Some examples of novel issues, they could be ones that you find on the site, such as pile design in unconventional soils or rock or carbonate soils. But you might also want to use novel design methods because you're looking at extra large diameter monopiles or you're using a different anchor type. So all of those things can be accounted for within certification and managed within a certification process. Other examples of selected novel design issues could include a different type of grouted connection, TP-less design, and other new connection technologies that are becoming available on the market. One of the things with a novel issue or a novel topic or something that might be problematic is to identify it as early as possible within the design basis process so that it can be given appropriate attention throughout. There's two main ways of dealing with them. The first is a project-based process, so you manage it within the project. You can raise it early, you can discuss it, how to resolve it. If it's an unconventional soil type, you might do a literature review to see what experience of that soil type is. For example, pile driving in gravel or something else can be quite difficult. So you'd investigate as much as possible, and then the project, the designers would make an informed decision that what to do, and then the certifier would also give an opinion on whether it was certifiable. So that there's a kind of a project-based process there. The alternative for something more novel is to use a more formal technology qualification approach, which might look at a different connection technology or a new anchor technology and assess that technology to see if it's ready to be deployed in the field on a commercial project. So the technology qualification process provides a formal framework to do that. And also within a certification process, it would be normal to capture the confidence in these engineering around these issues to make sure a successful outcome can be achieved, that the design is certified, but also that it will be successful in the end. This slide looks at what is often called Design Basis Part A. This is a design basis that contains all of the site condition data, and it's very often produced by the wind farm developer themselves to provide to all the other stakeholders in the design process, including the subcontractor, installation contractor, designer, etc. Certification of the design basis aims to confirm that the data has been collected in accordance with normal standards and that the data overall is suitable for the proposed wind farm development. The design basis contains data related to wind and meteorology, including wind distribution, extreme winds, temperatures, wind shear, turbulence intensity, etc. Contains metocean data in relation to wave and current loading, the different sea states, the water levels for design, and also any other criteria related to that. The next item is covered by geotechnical, which would include geophysical data, geotechnical data, most likely a ground model, and some description or study of seabed conditions and any hazards that we need to be aware of in the design process. It would also contain information on scour and seabed mobility, if that's likely to be important to a project. And finally, if the project is going to take place within a seismic area, it would contain seismic hazard design criteria. The final smaller part of site conditions is the grid connection, and that may also be needed to be included at this stage. To expand somewhat on the site conditions data, one of the primary components will be geotechnical data. And a sound understanding of the soil and seabed conditions is vital at an early stage to ensure that the right support structure concept is selected and confirm it's feasible for the site. The site investigation or the site conditions data usually results from the geophysical investigation and the geotechnical investigation, which I'll talk about more in a moment. And the output is often a ground model, which can be used through the design process. And that combines the geophysical data and the geotechnical data to provide to give an understanding of the site. More information on site investigation and the use of the different methods available can be found in a guidance notes published by the Society of Underwater Technology. And that's shortly going to be updated in 2021, and Lloyd has been helping to co-author that guideline. Just to refer quickly to the image on the top right there, it shows you a geophysical site investigation in process. But vessels are used with different types of equipment to scan and map the seabed, and you might also have ROVs and other types of technology working on that as well. Seabed hazards are often an important but sometimes overlooked aspect of wind farm site conditions. Geophysical methods are used to map the seabed, and it's important at an early stage that the geophysical data is examined to make sure that there's no features or hazards that could impact the development. Typical geophysical data includes bathymetry. It would also include sub-bottom profiles to see what the characteristics of the seabed is, whether it's rock, soil, soft clay. You'd probably have magnetometer data to check for any man-made obstructions, and you'd assemble all that data together and the output would be a geophysical report, and it's important to use that report correctly. What you might find within that report is a series of what are called seabed features, and they may or may not be a hazard. So an example of a seabed feature or a hazard could be mobile seabed, slopes, shallow gas or boulders. They're all natural hazards. Man-made obstructions might be unexploded ordnance or shipwrecks or other debris that's been dropped, shipping containers, for example. And you really need to go through the geophysical report and make sure you've identified all of those features and then understand the impact of those on your project. So the process that I often think of is to take the feature, you see if it's going to have an impact, if it's going to be a hazard to your project, and then you think about how you can avoid it, mitigate it, or engineer your way around it. And it's important to do this as soon as possible in the project. So really all of the relevant stakeholders should have the data available to them for the design process. An example which I encountered was where late in a project, the geophysical data was made available to the various parties, and it was found that there was a bathymetry variation across the jacket footprint. In this case, this was discovered at quite a late stage, and it took quite some effort to resolve, whereas if it had been found at the project planning stage, it could have been more easily handled and dealt with less concern or less trouble for all of those concerned. And the contour plot on the right hand side there shows the bathymetry variation across the jacket footprint. Whereas in principle geophysical methods are considered to look at the seabed but don't touch it, the next stage of the investigation is to mobilise a geotechnical site investigation to do some intrusive investigation into the seabed. That intrusive investigation could be drilling a borehole to obtain samples, it could be doing in situ tests down a borehole, or it could use seabed push equipment where you land something on the seabed and then you push from there to obtain a sample or perform a cone penetrometer test. One of the key considerations in defining the scope of an investigation is to think about what type of data you're going to require for your development. And that really depends on the foundation concepts that you're thinking about. And you should have an idea from the geophysical investigation whether you can use those concepts, what the engineering requirements of those concepts would be. So, for example, for monopiles and gravity-based structures, stiffness is very important. A little bit less so important for jacket foundations. You also need to think about the variability of the site. And what the soil types are and whether or not, for example, you might encounter rock. The two pictures on the right hand side there, the top one shows a fairly simple seabed. So there's some variability in the thickness of the layers, but it's not, and that variability has different impacts. So you can see the gravity-based structure, there's less impact on that of the top layer. Whereas for the jacket, the piles might have a change in end bearing and the jack-up might have different requirements for data. The bottom picture shows a much more variable seabed, and that can have very different impacts on the engineering that takes place. So that really needs to be considered when you scope an investigation. You can then use laboratory testing to calibrate the ground model and also to interpret any in situ data, and the final stage of that is to try and provide design parameters. So design basis part A has assembled all of the site conditions data, and the next stage in the process is develop a design basis part B. Very commonly this is done by the wind turbine supplier. And you can expect to see the type of things shown on the slide there to be provided in a design basis part B. So things like codes and standards, the environmental conditions that would be applied to the wind turbine RNA tower design, what the WTG is going to look like, the design procedure that will be employed, what sort of software model is going to be used, the load cases that will be defined, and what post-processing will take place. So design basis part B would then be shared with the other stakeholders in the process, including the developer and the substructure designer or support structure designer. So this slide shows some points which are often important to be considered within a design basis Part B. And one of those is that whether or not the wave conditions have been taken into account by the wind turbine supplier, who might be more focused on wind loads. The other thing is how the wind turbine supplier interface with the foundation designer, who equally might be more focused on wave loads. Also, things to consider include any turbine-specific failure modes and whether the failure modes have been then considered further in the load cases. Another interesting point, in particular for floating wind turbines, is that 6 degrees of freedom have been considered, rather than just the normal 3 degrees of freedom that you'd use for a fixed structure, and that the load cases are sufficient for each case, and also the relevant partial factors have been included. And on the right hand side there's some typical failures, and one that has come up recently is whether or not the wind farm is equipped with a backup generator in case there's grid loss during extreme weather. Design Basis Part C should outline all of the methodology and assumptions that will be used in the design of the support structure. Setting out these assumptions now can have a big impact on costs or schedule later in the project, therefore it's very important. And consistent definition of codes and standards and design requirements is also useful for all of the stakeholders involved in the project. And they include things like the wind turbine RNA and loadings from the wind conditions, the structural design criteria, grouted connection, design life, what partial factors will be applied, etc. Material selection and welding philosophy and corrosion protection, and then more geotechnical topics including scour, capacity, stiffness, and how the foundation will be constructed. It's also important to make sure that the Design Basis Part C thinks about all of the different phases that will happen during the support structure's life. And these include manufacturing, transport and installation, commissioning, in-service, and also decommissioning finally. And it's also good to consider the impact of the assumptions and whether they impact the capex at the start of a project or during the construction versus the opex, operational costs during the life of the turbine, and how they fit up with what the project needs. And we'll go into an example of this on the next slide. So the figure on the top right is a sketch of scour that may affect a wind turbine structure. So you can see there that the seabed has been washed away from around the structure and the piles. And scour is an issue that can be capex, so you could try and design for it and have the costs at the start of your project, either by including scour protection, so you try and eliminate scour, or you make a big design allowance and demonstrate that your structure is capable of withstanding a lot of scour. And the other way to think about scour is that it could be an OPEX issue. So that, in other words, you depend on inspection, possible management, remediation during the structure's life. So clearly those two different thoughts have different, you spend money at different times. So, and the project and the design basis needs that defined quite well early on. Another topic to consider on the bottom right there is whether there'll be jackups used during the construction or during maintenance of the wind turbines, and especially if the seabed is soft and the spud cans could have interaction with the structure foundations. This could become a problem later, but equally, if it's recognised at an early stage, then you can design for it or mitigate the risk of using jackups near to the foundations as early as possible. Another key aspect is to make sure Design Basis Part A contains minimum design temperatures, because these have quite a big impact on things like material selection later in the project. And in that respect, we often find that Design Basis Part C contains a lot more information on material selection than you might typically expect for that stage of document. The other thing is to recognise which material standards you're going to select and whether you take an EN approach or a DNV-GL standard approach, or in particular, if we try and mix and match between those, it can cause problems later in the project. So again, it's good to define those quite closely at the design basis part C stage. And also, of course, clear definition of the design life is important for planning corrosion protection and the protection that will give to the structure throughout the design life. So it's important to make sure all of these things and more is really clear at the design basis stage to avoid bigger, more costly problems later, either late in the project or during the service life of a structure. This presentation has given a summary of the offshore wind certification process and how the IEC and IECRE standards are applied to give project certification. Certification can provide assurance that a wind farm is being developed in accordance with the requirements, and it can also give assurance to stakeholders such as developers, investors, and also designers that the process is proceeding in accordance with international codes and standards or national regulations. One of the most important aspects in certification and offshore wind development is to make sure that the design basis is right at an early stage. And resolving things at an early stage can avoid problems later in a project that might get much more expensive or take a while to resolve. And certification has a role to play in that. More details on the topics discussed today can be found in Lloyd's Register guidance notes, of which the reference is given or the image of the front cover is shown to the right. Finally, I would like to thank you for listening, and we would welcome any questions or feedback you have on the presentation or to discuss offshore wind development in South Korea. Contact details are given on the slide here. Thank you for listening.